Hello candidates, and we are still organising, visualising and describing data, but now we're going to turn our attention to location and dispersion. We're going to start off with location, talking about quantiles, and then we're going to go into measures of dispersion, talking about things like range, mean absolute deviation, variance and standard deviation. Okay, without further ado, let's turn to our first slide. So our first learning outcome statement here says calculate quantiles and interpret related visualizations. So what is a quantile? Well, a quantile is a value at or below which a stated proportion of data in a distribution lies. So let's take the example of quartiles. Now with quartiles, what we're doing is dividing up our data set into quarters. Let's have a little look at an example of that. So visually, we'd have again, we're going to range our data from lowest to highest. And we've got the bottom 25% of observations. We've got the top 25% of observations. But of course, we've got the next 25% above the bottom here, and the next 25% above the middle here. Now, where are the first quartile, third quartile, second quartile, and fourth quartile? Well, first quartile is this value here. So 25% of observations will lie below the first quartile. The second quartile is this point here. So notice 50% of observations will lie below the second quartile. The third quartile is this value here. So 75% of observations lie below the third quartile. And finally, the fourth quartile is up here. So 100% of observations lie below the fourth quartile. Okay, let's return to our slide. So as we just saw in our diagram, 75% of data points are less than the third quartile. Now that's all right with quartiles, we're dividing up into quarters. But rather than dividing up into quarters, we could divide our distribution up into tenths, in which case we're talking about deciles. And notice 60% of the data points would be less than the sixth decile, 50% of data points would be less than the fifth decile, 40% of data points less than the fourth decile, etc. Rather than looking at tenths, we could look at hundredths. So take your distribution of data and divide it up into hundredths, in which case we are now talking about percentiles. Now, of course, notice therefore that 50% of the data points are less than the 50th percentile. And the 50th percentile is the median. Now remember, when we're dealing with an odd number of values, the 50th percentile will be the middle value when you range your data from lowest value to highest value. Remember, that was our definition of median in the previous module. Another thing we should be aware of before pushing on here is the interquartile range. Now notice the interquartile range is the third quartile minus the first quartile. So the third quartile, 75% of your observations, and again, remember, we're ranking from lowest to highest here. Okay, so 75% of your observations lie below the third quartile. 25% of your observations lie below the first quartile. So the interquartile range is giving you 50% of your observations, and it's the middle 50%. Again, if we were to go back to our diagram, where we were looking at our quartiles, here is our interquartile range. Okay, the middle 50% of observations. So third quartile minus first quartile. Right, so let's have a little look at examples. It says, what is the third quartile of the following distribution of returns? So notice we've ordered our returns from lowest to highest, and of course that is our starting point. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations. Okay, now we're going to use a formula. Ly, our value, okay, is equal to n plus 1, number of observations plus 1. So we had 10 observations, so this will be 11, times y over 100. And this y is our percentile. Now we want the third quartile. Now notice here it says percentiles rather than quartiles. So third quartile in percentage terms, 75% of observations. Oh, for some reason my pen didn't really work there. 75% of observations lie below that third quartile. So y will be 75 here. Okay, so we're going to use our formula. So we've got 10 observations, so n plus 1 becomes 11, and then we're going to multiply it by 75 over 100. Okay, 75% of observations are below the third quartile. We know that. So notice, 10 plus 1, 11, times 75, we get 8.25, or 8.25 of the observations. So what we're going to do is go along. Observation 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 18 is going to be critical for us. But what does the 0.25 mean? Well, we're 0.25 between the 8th and 9th observations. Okay, so there's our 8th and 9th observations. Let me just remove my ink here so you can actually see what the text says. Okay, so essentially we're 0.25 between the 8th and 9th observations. So we're going to take our 18%, the 8th observation, and we're going to take a quarter, 0.25%, between the 8th and 9th observations, which of course between 19 and 18 is 1%, so 0.25 of that is 0.25. So 18.25% is essentially our third quartile in this example. Right, we were asked not only to be able to calculate quantiles, but we were also asked to visualize them. And what we've got here is our box and whisker plot. Now notice we've got the smallest observation recorded here on our box and whisker plot. Okay, and that's very close to 0. And our largest observation up here, which in this case is very close to 100. And the distance between the smallest and largest observation is going to be referred to as our range. But what we're then going to do is mark on it a central portion of data. And here we're going to use our interquartile range. Now remember, middle 50% of observations lie in our interquartile range. So we've got our middle 50% of observations. And you can see we've also recorded the median on here. And we can see that our mean is slightly bigger than our median. So what can we actually tell by looking at our box and whisker plot? Well, notice the distribution, and this of course must be, if the blue shaded box is our interquartile range, this must be the top 25% of observations, okay? Whereas of course this must represent our bottom 25% of observations. So notice there's more dispersion, okay, in the top 25% of observations than there is the bottom 25%. Notice as well that my mean is above the median. All of this combines to tell me that there must be the presence of large positive outliers. We're going to see in a later module if your mean is above the median. Typically that's because you've got large positive outliers that are pulling your mean up. Remember what we said earlier, the mean is more affected by outliers than the median. So if the mean is above the median, it's often an indication of large positive outliers. If the mean is below the median, then it's often an indication of large negative outliers. Here we can very clearly see we've got a much bigger dispersion in the top 25% of values in our distribution than we do in the bottom 25%. So there is a box and whisker plot. Okay, our LOS changes now. We're now calculating and interpreting measures of dispersion. Okay, so we're looking at how our data points are dispersed normally around the arithmetic mean. Now the first one that we've got here, notice we've got some annual data here. We've got 30%, 12%, 25, 20 and 23%. So we've got 5 observations. First thing you might need to be able to calculate for the exam is the range. And of course the range is simply the largest value minus the smallest value. So our largest value here is 30%. Our smallest value here is positive 12. So we've got a range of 18. Okay, now of course be careful because in some distributions you may have a negative value. Let's imagine that was minus 12. Then our range of course would be 30% minus 12%. Okay, in which case it becomes 42% our range. Remember, if you have 2 minuses, it becomes a plus. So range, very simple to calculate. It's the difference between the largest and smallest value. But it doesn't really tell you how the data is distributed. It just tells you the kind of distance from largest to smallest value, but it doesn't tell you whether the data is clustered close to the arithmetic mean or distributed far away from the arithmetic mean. So we then turn our attention to mean absolute deviation. This is going to tell us the average of the absolute values of deviations from the mean. Okay, so this is first of our key measures that tells us about distribution around the mean. Okay, so we're looking at absolute values of deviations from the mean. What do we mean, deviation from the mean? We look at a particular value in our data set, let's call that xi. We compare it to the mean value, okay, and then we're going to sum that for all observations. But remember, we talked about a problem with that earlier on. We said 50% of observations by value are above the mean, 50% of observations by value are below the arithmetic mean. So if you do that, it's going to add up to 0. So how is mean absolute deviation going to get around that problem? Okay, well, let's have a look at the example to see this. Notice, first of all, we've just simply calculated our arithmetic mean by summing the values 30 plus 12 plus 25 plus 20 plus 23, and then dividing by 5. Okay, and that gives us 22%. Notice then, MAD then starts doing this computation, looks at each value and subtracts the arithmetic mean. So 30 minus 22, that gives us plus 8. 12 minus 22 gives us minus 10. 25 minus 22 gives us plus 3. 20 minus 22 minus 2. And 23 minus 22 gives us plus 1. Okay, so notice 8 minus 10, that's minus 2, plus 3 equals 1, minus 2 minus 1 plus 1, it equals 0, just as we said. But notice you've got these straight lines either side of a value. Now what those straight lines mean is simply ignore any minus signs. In other words, treat minus signs as positives. Okay, so what I'm going to do essentially here is treat that as plus 10, treat that as plus 2. So I've now got 8 plus 10, 18, plus 3, 21, plus 2, 23, plus 1, 24. And let's just then divide that by the number of observations, which is 5, to get the mean absolute deviation. The average distance, if you like, the average deviation away from our arithmetic mean. Okay, and you could be asked to calculate mean absolute deviation in your exam. I have to say, in the real world, it's a pretty rare computation. I haven't seen it ever in the real world. In the real world, we tend to use standard deviation as our classic measure of distribution or deviance, if you like, away from the arithmetic mean. And we're going to look at that right now. So we've got sample variance and sample standard deviation here. Notice that standard deviation is simply the square root of variance. So notice we start off exactly the same way as we did with our MAD calculation. We're going to look at the variable and subtract the arithmetic mean. But we know the problem is if we sum those, they're going to add up to 0. But variance has a different way of getting rid of the zeros or the negative values. What it's going to do is it's going to square the deviations from the arithmetic mean. Now, of course, when you square a negative number, it becomes positive. So this gets rid of our problem of negative values and the sum being 0. Okay, notice we then divide through by n, number of observations, minus 1. Now, this gives us sample variance. Population variance, given by sigma squared, is equal to the sum of xi minus x bar. Well, I should actually use mu for population mean, shouldn't I? Let's be correct here. So again, observation minus population mean squared divided through by n, the number of observations. Okay, but notice when we're looking at sample variance, it's n minus 1. Now this n minus 1 is something known as Bessel's correction. And it really gives you an idea of what sample variance is trying to do, what it is if you like, and what it isn't. Now what it isn't is the variance of a sample of data. If we were just simply trying to work out the variance of a sample of data, we would use this calculation here. So what the heck is sample variance then, if it's not the variance of a sample of data? Well, what it is the estimate of the population variance coming from a sample of data. Now, what Bessel said was, if you were to just take a sample of data and take its variance and say, oh, that's equal to the population variance, you would be essentially underestimating the true population variance. Why is that? Well, your sample is less likely to contain extreme outliers than the population. So what the n-1 is doing is pushing the sample variance up. It's increasing the sample variance because the sample of data is unlikely to contain the outliers. So the idea is sample variance is a better estimate of the true population variance than simply taking the standard deviation or the variance of the sample data. Okay, so notice when we move on to standard deviation, all we're doing is looking at the square root of variance. Now, variance is very useful mathematically, but it's quite difficult to actually interpret. Theoretically, it ranges from negative infinity to positive infinity. So theoretically, I shouldn't say negative, I should say it theoretically extends infinitely. Okay, so it's quite difficult to interpret variance, but standard deviation is a lot easier to interpret. And the reason standard deviation is so much easier to interpret is because it comes out in units that your data set is measured in. So if your data is in percentages, your standard deviation comes out in percentages. If your data, let's say, is made up of measurements, so let's say it's in centimetres, then your standard deviation comes out in centimetres. If your data is number of glasses of wine drunk in a week, then your standard deviation comes out in numbers of glasses of wine drunk a week. Okay, so standard deviation has the same measurement scale as the data set itself, whereas variance doesn't. So variance very useful mathematically, standard deviation far more easy to actually interpret. And we interpret our standard deviation essentially as the average distance from the arithmetic mean. So both standard deviation and variance are measures of risk. They're measures of dispersion around a mean. Basic argument, therefore, is the greater the variance, the greater the standard deviation, the more dispersion you have around your arithmetic mean, and therefore the more volatile your data set is. Okay. Now let's calculate our sample variance and sample standard deviation. So our starting point is to calculate the arithmetic mean. So notice we've got the same data sets as our MAD calculation, so we're going to end up with exactly the same arithmetic mean of 22%. What we're then going to do, of course, is we're then going to look at the differences of our observations and that arithmetic mean, and we're going to square them. So 30 minus 22 gives us 8. We're then going to square that. That gives us 64. 12 minus 22 gives us minus 10. We're going to square that. Gives us positive 100. 25 minus 22 gives us plus 3. Square that. That's 9. 20 minus 22 is minus 2. Square that. Plus 4. And 23 minus 22 is 1. Square of 1 equals 1. Okay. So notice, therefore, our numerator now adds up to 64 plus 100 plus 9 plus 4 plus 1 adds up to 178. Now, if we were working out population variance, we'd then divide through by n, i.e. 5. But if we're asked for sample variance, remember we're going to make that Bessel's correction, we're going to divide by n minus 1. In other words, we're going to divide in this case by 5 minus 1, 4. Okay, so 178 divided by 4 gives us 44.5. We can work out the standard deviation by taking the square root of our variance, square root of 44.5. Okay, square root that, and we get 6.67%. And notice, therefore, it's coming out in the same units as our original data set. Okay, so because our data set were returns measured in percentages, our standard deviation comes out in percentage. And remember, what we're saying with standard deviation is it's measuring dispersion around an arithmetic mean. So the bigger the standard deviation, the bigger the average distance of your observations from your arithmetic mean. And remember, variance or distance of observations from an arithmetic mean is a measure of risk. Therefore, variance and standard deviation capture both upside and downside potential. In other words, variance above the arithmetic mean and variance below the arithmetic mean. Okay, so deviations both above and below the arithmetic mean. Now, I think you need to be aware that your BA2 Plus calculators can do these computations for you. I'll just quickly take you through that. Let me bring a BA2 Plus up on the screen. Here it is. So first of all, we're going to do second function and then 7, and that gets us into data entry mode. I then need to clear any data from my screen. Second function, clear equals cancel, and I've just stripped out any data. Okay, so you always do second function and clear equals cancel to clear any worksheets. That is the same for every function on your BA2 Plus calculation, apart from those time value and money buttons on the third row. To clear data in those, it's always second function and the future value button. Okay, so x01, it's asking me for my first x variable, my first variable, and that is 30%. Now you've got a choice here. You can either enter returns as decimals or whole numbers. I have to say, I think it's more correct, if you like, to enter as decimals. So I'm going to type 0.3 and then hit my enter key for 30%. Then press down, you'll get Y01. This is to do with frequency of observations, okay? Now, when you're looking at historic data, then you're going to leave that as 1. That 30% occurred in one period of time. Okay, so we're going to leave that as 1. Press down to get X02, 12%. So I'm going to enter that as 0.12 and press enter. Down, again, ignore the Y02, down to X03, and you've got 25%, so 0.25. Enter. Down again, X04, 0.2, and enter. Down twice again to get X05 and 0.23, and enter. Once you've got your data in there, we're now going to go into stats mode in the calculator by pressing second function and the number 8 button. Now notice my calculator has automatically defaulted to lin for linear regression. Now if I leave it in that mode, it's going to view my x variables as essentially an independent variable and my y variables as a dependent variable, and try and regress the two together. Okay, I don't want that. I've only got one variable here, the x variables, so I need to tell my calculator that. So I'm just going to change the stats mode by pressing second function and enter. Notice it changes to natural logarithms. Second function, enter, exponentials. Second function, enter, power. Second function and enter, 1 minus v. This is the mode I want on my calculator. This is telling my calculator, hey, there is one variable here, the x data. Now when I press the down arrow, notice first of all the calculator tells me n equals 5. In other words, I've got 5 observation. Okay, good. Then it tells me x bar. Okay, so the arithmetic mean of that data is 0.22 or 22%. Then Sx, and notice Sx is the sample standard deviation, so 0.0667 or 6.67%. Notice if I press my calculator down one more time, I get sigma x, and that is the population standard deviation, okay, rather than the sample standard deviation. People often get worried in the exam when to use sample standard deviation, when to use population. Well, typically I'm going to use sample standard deviation when I've got a sample of historic data. If I'm looking at forecasting and I've got X variables and then I've got the probability of those variables occurring and the probabilities add up to 1, then I've got 100% of all observations, and I typically use population standard deviation. Okay, so anywhere where we're using historic data, then we're really using sample standard deviation, so that's not relevant. Let's go back up one. We're using SX on our calculator screen. And remember what it is. It's the estimate of the population standard deviation using a sample of data. It is not the standard deviation of that sample. The standard deviation of that sample data is the 0.05966. Okay, we are looking at an estimate of the population standard deviation coming from a sample of data. Now, if I was asked to calculate the variance, all I need to do is take my standard deviation and square it. So there you go. There is the variance, 0.00445. Okay. Now notice there's a bit of a difference here, because when we did this, we got 44.5, but that's because we used whole numbers rather than decimals. Okay. Okay. So that means you're essentially a large number out by a factor of 1,000. So divide by 1,000 and you get it in decimals. I prefer to work in decimals. It's more mathematically correct. Okay. Okay, so there is our sample variance. Let me get rid of our calculator and then we can move on to our next slide. So our next computation is calculating and interpreting the coefficient of variation. Now, the issue with standard deviation is it's an absolute number, and it makes it very difficult to compare between distributions. So I've got two distributions here. I've got the distribution of T-bill returns and the distribution of returns on the S&P 500. Okay, and I've got their standard deviations, but they're not directly comparable. Why are they not directly comparable? Well, because their interpretation depends on the mean. Okay, and they have very different means. Okay, so we're looking at absolute figures in standard deviation, and they're therefore not comparable unless the two distributions had the same mean. So how can I convert them into a relative measure, which I can compare? Well, what we do is we calculate the coefficient of variation, and notice that computation is standard deviation divided by mean. Okay, so let's think about what this is doing. It's taking standard deviation and dividing by mean. Remember, we can think about mean as being the average return or the expected return. So what coefficient of variation is looking at is it's looking at risk per unit of expected return. Okay, now obviously I'd prefer to choose investments that have less risk per unit of return, and therefore a lower coefficient of variation is better. Now, I think some people get this the wrong way around. They think they're maybe looking at mean divided by standard deviation. And I think the reason they think that is because they're used to looking at the Sharpe ratio. And remember, the Sharpe ratio, what that looks at is it looks at a return on your portfolio minus the risk-free rate over the standard deviation of your portfolio. Excess return per unit of risk. But here, okay, that is not correct. Notice the correct way is we've got risk on the numerator and mean return on the denominator. So it's actually risk per unit of mean return, not mean return per unit of risk. Okay, so don't get it mixed up with the Sharpe ratio is what I'm saying here. Okay, so we've worked out the coefficient of variation for T-bills. Mean divided, standard deviation divided by mean, 0.36 divided by 0.25. That gives us 1.44. Then S&P 500, 7.3 divided by 1.09, 6.7. Remember, lower is better because essentially what we're saying here is we want less risk per unit of expected return. Okay, our last little LOS for this particular module is looking at target downside deviation. Okay, target semi-deviation it may be referred to as. Now, on the face of it, it looks like our standard deviation calculation. In fact, if this had been X bar rather than B, okay, it would have been very much our standard deviation computation. let's have a look at the differences. What we're going to do is really look at downside risk, the risk of not achieving some target value. And that target value is B here. So that B is equal to our target value. Oh, can't spell target. Now it could be the mean or it could be some other value. Now notice we're not looking at all observations on our numerator. We're only going to take observations that are lower than the target. Any observation above the target is ignored. Okay, so we're going to sum the deviations that are lower than the target value, square those deviations, sum them, and then divide through by n minus 1. Now again, we need to be careful with n. N is all observations in our data set, even the ones that we exclude because they're above the target value. Let's just do a computation with this. So here's our data, 30, 12, 25, 20 and 23. We're going to use a target of 24. So we're going to ignore any value that's above 24. So that gets ignored, that gets ignored. Okay. So there's our observations. We're going to ignore the first one and we're going to ignore 25 because that again is above 24. So when we're looking at our deviations, we're going to look at 12 minus 24, which is minus 12. We're going to look at 20 minus 24, which is minus 4. And we're going to look at 23 minus 24, which is minus 1. Okay, so we're going to take those deviations, which are all negative, because they're all below the target, of course. We're then going to square them, okay, and then we're going to put them over n minus 1. But n is all of these observations, and remember, therefore, we had 5 of them. The mistake candidates make is they think, well, actually, I've only used 3 in my calculation on my numerator, so I'll do n as 3, so 3 minus 1 on our denominator. No, it is all of the observations, including the ones that were above the target. Okay, so that gives us 6.34, where we square the deviations, sum them, divide them by n minus 1, so divide them by 4, and then take the square root. So remember, this is equivalent to a standard deviation. Okay, but it is looking at standard deviation of downside risk only. Remember, when we look at normal standard deviation, it is looking at deviations above the arithmetic mean and deviations below the arithmetic mean. Here, in target deviation or target downside deviation or semi-deviation, we are only looking at the values below our target. So it is downside only.